Good afternoon, participants. We shall now commence our afternoon session. Afternoon session will be engaged by Dr. P.H. Shekar on classification techniques, specifically on dimensionality reduction techniques and its implementation details. Before we commence, let me introduce the speaker of the session, Dr. P.H. Shekar. Dr. P.H. Shekar is currently working as professor in Department of Computer Science, Mangalore University, Bangalore. He is specialized in pattern recognition, image processing, machine learning, artificial intelligence, database systems, and data structures. His nearly 185 articles are published in international and national level journals and conferences. He has worked as a reviewer to Elsevier, Springer, and IEEE transactions. He has chaired sessions in national and international conferences and delivered special lectures on various occasions. He successfully guided 10 candidates towards doctoral degree, and currently 10 students are working towards their doctoral degree, covering video analytics. He was awarded Commonwealth Academic Fellowship during 2014 to carry out his postdoctoral work at University of Surrey, UK. The Sandwich Model Fellowship is awarded by German Academic Exchange Service during 2002 to carry out part of his PhD research work in University of Nuremberg, Germany. He has successfully completed international collaborative research project works with Moscow State University, Moscow, Russia, and University of Tokyo, Japan. He also conducted GIAN programs on digital payments technologies for cashless society and visual object recognition, funded by MHRD, Government of India, inviting Professor Joachim from Germany and Professor Raghav from University of Texas, United States. Apart from academics, he also worked in the administration as a special officer for about 4 years and worked as a director in charge of Computer Center. He has effectively completed various e-governance related administrative responsibilities entrusted by the administration during his tenure as a special officer and director. With this short introduction, I welcome you, sir, as the speaker of the session. Now I request you, sir, to start the session. Over to you, sir.
Thank you very much, Ganesh, for
sir.
the nice introduction. Professor Nagbhushan, in his keynote address, mentioned machine learning for societal applications. Obviously, when we are dealing with machine learning algorithms, so there are various issues to be known. Of course, the mathematics behind machine learning to be known to the researcher, such that they can find or explore their technology or whatever the methods so far developed onto different societal applications. There could be many, and it is already pointed out by the earlier resource person, a number of applications we can think of. And as you know, that government is also encouraging through these STTP programs and also ATAL programs, AI-enabled programs, and it is gaining attention in these days, making the machines to learn, and subsequently they can be used for what are called as the routine works, which certainly where human beings feel or tend to be tired. It could be visual surveillance and so on and so forth. Among the many what are called as the machine learning algorithms, so in fact principal component analysis is explored to the maximum extent by many researchers who are working in different fields. It is not necessarily to the field of computer science, image processing, pattern recognition, or machine learning. It is even explored in the chemistry, explored in the physics because of its significance in data extraction, meaningful data extraction. And on the first day, in fact, Dr. Ari Vinod has given you just a blueprint. I mean to say that a bird's eye view, how exactly we can use a scikit tool, scientific kit tool, provided in that what is called as a Python programming, where he has given what is called as a kind of black box. So he has used a function called, say, PCA, which does the task of what is called as a data transformation. But as a researcher, if at all you would like to continue your career and provide or make modifications or explore PCA for different applications, you need to know the internal details. And that is what this, in fact, STTP is aiming at. I mean, basically providing the fundamental details, basics of what are called as those algorithms which were available in the form of what is called as a black box. So it's in fact a very good, I mean, from the day one, I have seen Dr. Zahid Ansari has given an excellent input on clustering mechanisms. And there are tools, functions that are available to cluster the data automatically. But how, what is the internal details in order to cluster the data is most important. Similarly, Dr. Nagendra Swamy has pointed out in a morning session, has given an elaborate talk on classification techniques and how they work. How do I build an algorithm? So probably I expect all the participants to implement on their own all these what are called as the maybe each line of what is called as interpretation or mathematics, whatever that we have specified, should be represented in any of the coding language, either in C++ or Java or Python, of course, in the recent days gaining popularity. Even it is succeeding, even superseding Java also. Okay. And our programming language can equally be used, of course, as Zahid Ansari has pointed out earlier. And particularly, I feel it is more suitable to business data analysis. And whenever there is a large amount of data, definitely R excel in terms of when it comes to the Python. And Python is a kind of interpretive language, provides a lot of features to the research community, and provides set of functions. And it is keep growing, of course, as you know that particularly within the framework of Anaconda, people are exploring to the maximum extent. And probably by this time, many of you might have looked into GitHub, where researchers tend to provide their code, which would be useful to the research community. And I'm sure even whatever that we tend to discuss over here also, some part of the code is also taken from GitHub. And I insist the fellow participants who are beginner, probably if they are carrying out a research work start now or in the line of research, may refer to GitHub for most of the programs that are available over there. And PCA is one such. We will see the internal details of the principal component analysis. Why it is called as a PCA? What are the reasons? Where do we find the applications? I mean to say that we basically go for discussing the following aspects. What is the motivation? And what is the theoretical aspects behind principal component analysis? And finally, after discussing the theoretical concepts, we can go for the algorithmic representation. In fact, finally, what we are intended to as a computer science person. So how exactly I can map these set of what are called as theoretical concepts to set of steps, which will give me what is called as a refined data. So ultimately, it is a data transformation algorithm. But what kind of data transformation we will see? And the applications are many. It could be in the domain of face recognition, image compression, and in what context face recognition is useful. Definitely, it is very apt with respect to what is called as the course, what is so far designed, STTP, machine learning for societal applications. When I say it is a face recognition problem, I'm sure by this time, most of you, I think all of you are explored what is called as this face recognition as a part of a simple smart device to open, say for example, to unlock that, I can think of what is called as unlock the mobile smartphone, maybe through what are called as face or say a fingerprint. And it is now, of course, no more it is a common, even in the industry also, to take the attendance through the, and even in educational institutions also to take the attendance through the faces. I mean, it is one kind of definitely very well explored problem in the society for better living, if I say, in the sense that automated data management will be more easier if I go for such kind of what are called as the machine learning based application. At what time you logged in, at what time your ward or child logged in, say for example, to the school, the teacher, whether engage the classes or not, things like that. I mean, we can coin different problems, of course, when I consider what we are facing in the, I mean to say that from the point of view of data management, maybe to the dashboard, say for example, as a parent, let us say, those who are seniors over here, definitely they would like to know whether the children are going to the school and attended the classes regularly or not. They can easily make out that. So using such technology enabled solutions. So even for a teacher also, even to manage the attendance and all those things, they can think of these kind of parameters. In addition to that, PCA also finds, particularly it explored a lot in the domain of what is called as image processing. So maybe image compression. So to effectively use the bandwidth. So probably, as you know that you might have compared various what are called as the tools in order to work with data transfer. Zoom is one such, which basically takes a less amount of what is called as the bandwidth when compared to the other tools like WebEx or so. WebEx maybe, say for example, if I take 100 MB, normally Zoom takes say less than 25 or so in order to transfer the data from other place. But that is again technology enabled. Some kind of compression mechanism would have been built. Maybe PCA can as well be explored. Similarly, denicing. So denicing is where in which the data that you are going to capture may not be always noise free. So in real environment. In such cases, we can think of what is called exploring this PCA for that. And kernel PCA is an extension of the principal component analysis where we are going to classify the data in non-linear sense. So and finally, I would like to give a demo on this principal component analysis using Python Spider tool, of course. So finally, it is the summary. This is the overall presentation of what we have planned today, and I hope within this schedule allotted time, you would be able to discuss all these things. So what basically, I think these, as a review or a recall, we would say, and I'm sure these definitions is already been dealt and discussed with you by our earlier, what are called as the resource persons. So they already mentioned what basically machine learning is for. So I just wanted to point out here one such what is called as the statement. So the statement which says a computer program is said to learn from experience E with respect to some class of task T and performance measure P if its performance at task T as measured by P improves with experience. So you can just analyze this particular statement from the point of view of workshop also, the STTP, what you are undergoing. It means to say that if you got something from this workshop, so definitely it means that you learned something. So that is what I would say. If the performance improves for a given different task, when maybe you are attending some other what is called as a course, maybe in some other place, you can in advance you can give the inputs to the resource people. Happen to be the case, that may be the case. So it means that you are experienced and made it more possible. So, and it is true in almost our learning environment. I mean to say that in the way that we are learning, can I make the machines also to learn? Can I advance their learning through an experience? That is, of course, a very complex job, particularly making the machines to learn. In fact, in the keynote talk, as Professor Nagbhushan pointed out that whenever I train a machine, it is for a specific task, unlike human beings. We can do many things simultaneously. It's an excellent, what is called as a parallel processing tool. However, and also execute many jobs. But if at all I need to devise such AI-enabled, intense machine learning enabled system, so it is very, very complex process. You take, for example, anything, what is available today, it would be a cleaner, or it could be an Alexa tool, which understands your, what are called as the statements or so language, natural language processing kind of stuff. And they are meant for a specific job. They cannot do all the things. Or driverless, what are called as the cars. So autonomous vehicles, what you would say. So whenever I need to devise such systems, they meant for a specific job. But as far as the human beings are concerned, definitely they can do multiple jobs. Although it is quite difficult to replace the human beings by the machines, we tend to apply or explore this technology for day-to-day activities. And large amount of data is there. Definitely, it's quite difficult for the human being to analyze large amount of data within a reasonable period of time. So therefore, can I think of exploring some kind of what are called as the data learning systems? So and such that I can take a decision within a reasonable period of time. Business analytics or surveillance system, tracking a person or sanctioning a loan. So many are there. Nagin Swami in the morning session has discussed whether a person to be sanctioned loan or not, or to play cricket depending upon the weather conditions, can I take a decision? So taking the data from the sensors, which is a part of, I would say, an IoT, taking the data from the sensors, sitting at home itself without going outside, you can take a decision. Such intelligent decisions can be made with the help of what are called as the machine learning tools. In a way, the goal of machine learning is to build a computer system that can adapt and learn from their experience. Ultimately, that's what we are trying to do over here. So different algorithms have been developed in order to make the machines to understand and subsequently the react. And what are the different kinds of algorithms that are available? And as you know that, as it is already discussed, the different kind of algorithms would be either a supervised learning algorithms or unsupervised learning algorithms. So when I say it is a supervised learning algorithm, it is nothing but a classroom kind of environment, as you know that. So in the sense, a teacher guides you and subsequently you will take a decision. And then similarly, I would say in the home environment, maybe a mother teaches are taught what to be done, what not to be done to a child. Definitely she will guided by someone else. That would be the case. I mean, you can give many examples of that kind. And can I devise, or there are different, particularly broadly when it comes to machine learning, these are the different, two different approaches. When I don't have a knowledge of the environment, probably I can think of unsupervised learning algorithms. So in this way, of course, when I consider different problems of what are called as the machine learning algorithm, say for example here, digit clustering and say a recognition. So you know that as you can see here, two people write the same digit in different ways. And this problem, in fact, is a well-known problem in the earlier days, even today also, because of the complexity that is involved. When you start working, definitely will realize how much complex it is in order to devise an algorithm which understands the handwritten data. So even today, people are working on that. Although it's a well-addressed problem, which would probably our own professor from India established a CIDAR laboratory in US, Sargur Srieri. He worked on this postal automation issue, where he has taken, to say that pin code, based on the pin code, automatically the mail sort is being carried out. And that is again based on these analyzing or classifying these digits. So mail sorting is one of the earlier days a complex problem. And later, nowadays, of course, it is replaced by a technology. Maybe we will have the email system or WhatsApp, many things are there. But still, there are situations where we need to personally look for what are called as the postal services. In such case, as you know, maybe you may not aware, the present generation, in the earlier days, the postman should go to the post office very early in the morning and classify based on the pin code, and subsequently the people will collect, and then the remaining people will collect, the remaining postman people will collect and distribute the same to different places. So such, it is again a classification problem. So if at all, can I automate that particular process? Of course, it boils down to what is called as the data, what is called as the symbol recognition, digit recognition also. So what is the basis for that? So the basis is to collect all different kinds of samples so that the system can learn, and subsequently given a new sample, then it is able to classify to which class it belongs to, whether it is a digit 1 or 2 or 3 and so on, 9. So, and while learning, it is supposed to look for the account of variability in writing style. As you can see here on this slide, the letter 1 or say, the digit 1 or say a 7 or say 5 or say 8, different in different style. Maybe its orientation is changing. Even though there is a change in orientation, please note it is a very complex problem. In fact, Even we too have experienced when we start doing the research work. And in fact, Professor Guru has made us to realize how difficult it is when you have a problems with noise with the data that we have collected. I will tell you at the later stage how complex it is when there is a noise in the data. And it is true here too. Might be say for the human beings, it is very easy. We can easily understand the orientation. But if at all I want to make the machines to understand, irrespective of the orientation, whether it is what letter is, what digit it is, it's a complex process. But in not all situations, orientation is important. For example, digit recognition problem you consider. I take 6, then again 9, and if you make it a rotation invariant, it is going to be a problem. Because if you take the, I mean, exactly the 90-degree orientation, then it is going to be 180-degree orientation, it is going to be a problem. So therefore, depending upon the application in hand, we need to look at whether invariance is required with respect to such what are called as the linear transformation. Therefore, sometimes you also need to know about, in order to develop machine learning algorithm, probably linear algebra is playing a significant role. So maybe you can take it as a first course if at all you happen to join as a researcher to the field of pattern recognition, image processing, or machine learning, or artificial intelligence for that matter. Like this, we can keep on coining different problems. Say, for example, it could be a document analysis problem. How can I develop the algorithm that produces a summary of the document? And how do I say the two documents are similar? And it is a well-known problem now in the society. You know that there are what are called as the predatory journals. How do I avoid such duplication of the work to be published in the journals? And there are standard tools that are available nowadays, where in which I can easily say what would be the amount of plagiarism in your document. If it exceeds 30% or so, probably in the first stage itself that gets rejected. So, I mean, we are looking for the similarity of the document. Then what kind of features that you are going to extract? Similarly, in the previous, what kind of features that we are going to consider as far as the digits are concerned? It is most important. Because when you extract discriminative features, that is of course required, but it is not always possible to extract the discriminative features. So can I get discriminative features from the set of all possible features? That's a question. We will see is principal component analysis is a solution for such kind of problems. Similarly here, when I look at, of course, document analysis, where predict document layouts that are suitable for different readers. In fact, this problem was given to me earlier by Professor Nagbhushan to start working on that. In fact, I could find extremely difficult, and later on I talked to Guru, you better take some other problem if you are finding difficulty. And that is the first thing that you need to do as a researcher. Take the problem which can be very well solved. That is most important. Don't take too much complex oriented problem and try to solve it, because you are supposed to come out with a solution within a reasonable period of number of years, maybe 3, 4, 5 or 6 maximum, like that. So therefore, I request the researchers, beginners probably, you want to look into the feasibility analysis of the problem that you are going to take up. Predict document layouts that are suitable for different readers. What do you mean by that? I mean, how exactly when you say, for example, you are going in a train, then paper might be folded in different ways. Then how do I organize the content such that it is readable? So in fact, the newspaper, when I am generating a paper, probably in the previous day, those people will work. What would be the template that is best suitable such that I can get the contents? Placing the contents onto the say paper is also a significant research work, although they may do it unknowingly. In fact, they give a best layout so that what is called as the reader can very well be say that happy with the presentation. So presentation is most important, even in our lecture presentation also. How well we organize the content so that the reader or the listener can understand, can interpret. And that is most important also. In fact, you are expecting the same teachers are here. I'm sure you are expecting students or to come out with a best presentation, because that carries, that matters a lot. And similarly, in the case of document analysis too. Of course, I already mentioned about the biometric traits, and these are the different biometrics and what kind of features that you are going to take. When I say it is a features, as you are already aware that it is nothing but characteristics of the data. And right now, I am focusing only on the image data. It is not necessarily the data could be of image type. It could be a text. It could be a speech. It could be again video multimodal in nature. That may be the case. It could be the environment data that you are going to take. It could be a sensor data, and the data size would be very large. So when you take up these what are called as these biometric traits, either a face or a fingerprint or an iris or a voice or a 3D face, can you imagine what may be the dimension of this data? If I consider the face itself, say for example, of the same size, then it is a matrix because probably some of you already studied digital image processing. If I say it is ultimately it is a matrix representation of the image data, two-dimensional representation of the data. I'm sure it is of size 100 by say maybe 200 by 100 or 120 or 140 or so. So in our regular studies, I'm sure we have not taken up such a image or a matrix of size 200 by 100. It's very, very large. So to deal with, and can I identify which are more significant? I mean, in ultimately when I say it is a matrix representation, it is again the intensity values. And what are the intensity values that are important for me? Is it possible to analyze? Definitely not. So we may need to, of course, depend upon some kind of what are called as the algorithms that understand what is called as variability in the data. And can PCA help in that direction? We will see how exactly I can think of extracting the features given an image of size m dimension, whatever it is in general when I say. So this finds, of course, several applications, as you are very well aware of that. And I'm sure these are the most popular traits among the many biometrics data. Fingerprint that is used in almost all the engineering colleges nowadays to get the attendance. Face is used for mobile unlocking. Even one of the most notable work by the Indians is the creation of what is called as the Aadhaar database, where they collect your face, the fingerprint, the iris, all 10 fingerprints, etc. That gets collected. I don't know, speech of course may not be included, and such amount of data is collected, and it is a very vast, huge information to say. And face is extensively used, and similarly iris, although iris is an excellent what is called as the method, or say sorry the data implementation or say cooperation from the users would be too difficult. Even fingerprint cooperation sometimes is required, sometimes may not be required, but as far as the face is concerned, cooperation may not be required. So therefore, you have seen a lot of works where in which we are using face as a means from the point of view of data classification or data clustering. That would be the case. I mean, NIST is there to give you the standards on such data too, anyway. And the nature of data, as I already told you, not necessarily to the image, and image not necessarily to a binary image. As you can see here, it could be a binary image, or it could be a grayscale image, or it could be a color image, or it could be even the video also. So what is the amount of data that we are processing? In fact, the amount of data that we are processing is in terms of so megabytes, terabytes, or say gigabytes, which we cannot imagine. So for the bare eyes, for the human beings, definitely it is very, very difficult. So as far as my experience is concerned, as far as the systems are concerned, it is very, very difficult to obtain what is called as or interpret or information from the given what is called as this matrix representation of the image data or the video data. So therefore, we research to what is called as the analyzing these what are called as the patterns. So ultimately, it boils down to any kind of applications that you take, be it a bioinformatics or biometrics or text processing, etc. We are looking for some patterns. So what kind of pattern that particular image process? To understand the scene also, for example, I would like to say this is a laptop and there is a mobile device, or there is a desktop, or say there is a kettle, or there is a cat, etc. whatever I'd like to say, it depends upon our what is called as the experience that we have learned over the days. And it is the letter or it is the digit, etc. Also, if at all I want to say. And an illiterate cannot say that. What literate is, definitely they are unable to, because they were not trained. So means to say that I am trying to train a machine with given set of pattern. So it may be a face pattern, it could be a barcode, or it could be a fingerprint, and so on and so forth. It could be a letters, or it could be simple geometrical figures, geometrical objects. Earlier days, in fact, people tend to work in the initial days in the field of pattern recognition on these kind of geometrical objects. So, and subsequently nowadays, as you know, that it's excellent growth. So in the sense, we are trying to develop a pattern recognition system that simulates the human thinking. That is, the real power of human thinking is based on recognizing pattern. Can the computer do better than that? In fact, it is a question. So, and we are trying to simulate that, simulate the human thinking. In the earlier discussion also, in the keynote address, Professor P.N. sir has pointed out, is it possible to simulate the human brain? So it's very, very complex process. It involves different, it's purely an interdisciplinary. I mean, cognition, recognition issues are also there. And ultimately, as Professor Guru pointed out, it is searching for patterns in the data. When I say it is a searching, it's again a kind of algorithm that we are looking for to search for a particular pattern. That is, the problem of searching for patterns in data is a fundamental, and it is a long successful history. As far as AI algorithms, based algorithms also concerned, so search is playing a significant role. For example, I want to play a chess. So it's all possible moves has to be simulated, and subsequently I can think of whether it is possible to win the game or not. And that's where that particular IBM Deep Blue gains a popularity, and it wins over the a champion during those days. So I mean, ultimately, it is an act of taking the raw data and taking an action based on category of the pattern. So what we have seen in all these days discussion is what is ultimately we are taking some raw data and classifying that raw data onto a given class, whether it belongs to a particular class or not. So in the sense, we are trying to analyze the data. So when you are analyzing the data, obviously the question that comes to your mind is it necessary to look at entire amount of information? Or is there any possibility? In a way, when I say, for example, given an object, I take out its intensity information would be the simplest feature extraction mechanism. All the intensity values of a particular image data would be the simplest feature extraction mechanism. Can I take all those values, or can I take only the abstract representation of the data or meaningful information from the data? And how do I compute, how do I obtain a meaningful information from the data is a question. So is there any possibility to find out the strong correlation between the features? Is there any way to find a smallest subspace, okay, that keeps the most information about the original data? So how do I extract or find out a smallest subspace from the large amount of what is called as a data space, which retains the maximum variance? And you know, when the variance is zero, what is the inference that we could draw? In fact, it is an online session. I cannot get even feedback from you also, because all of your microphones are muted. So I would say that if the variance is zero, it means that basically, let's say if the variance is zero, then there is no difference as far as the deviation from the mean is going to be zero. And in such cases, it is, of course, all the data are almost one and the same. That's what the kind of inference that you could draw. So in the sense, can I have, suppose if there are such features, I can as well eliminate them. But in reality, in general, it may not be possible to have such scenario. So definitely I cannot think of having, but we tend to, I mean, when we are framing what is called as the theoretical framework, we assume in such what is called as the information over here, constraint over here. So what would be the solution? In fact, I mean, the solution is available through what is called as the principal component. All these background that I had given is basically from the point of view of data analytics issue. I mean, we have just taken some simple applications, the examples, the data sets, where the amount of data that you are going to handle is m dimension in nature. Large, m is very, very large. For example, if I consider 100 by 100 size image, maybe it is 1 by 1 square centimeter as far as fingerprint is concerned in such case. Or your signature, maybe what is called as a 30 by 80 would be the case. So then it is going to be 2400 dimensional data. So if at all I consider such huge amount of data, is there any way such that I can retain what are called as the best subspace which represents the original data? So what is the mechanism, or can I find automatically a solution? I mean, it's not possible to simply chop off the vectors. So I mean, sorry, the what are called as the values. So I should find some transformation function which transform the data from higher dimensional to a lower dimensional space. Sometimes, therefore, this principal component analysis is also called as a dimensionality reduction technique. So Professor Guru sometimes may not agree with me when I say it is a dimensional reduction, because he would argue tomorrow. I am sure there is a class by him on feature selection. I am sure he will point out these things. Feature engineering, which is an excellent area, although nowadays, as you know that, which you are going to learn in Friday sessions, deep learning, which extract the features, then why feature engineering or feature selection is required. And there are reasons to go for what are called as the feature selection, feature extraction mechanisms, where deep learning fails. Anyway, we will have such discussion with Dinesh on that day. Okay. So coming to this PCA, what does it do theoretically? So it's an orthogonal projection of data onto a lower dimensional linear space. It's basically a matrix algebra, nothing more than that. What does it do? It's basically maximizes variance of the projected data. As you can see here, the purple line. I have a what are called as set of two-dimensional data points over here, represented with red dots. Okay, represented with red dots. So, and when I compute what is called as with respect to these spread of data, the data spread, as you can see here, along the principal direction in this way, and of course perpendicular to that would be this away. And when I project these what are called as red dot points onto what is called as this principal direction, then definitely I get a better separability. So that's what you can see here. And as you can see here, I am projecting this dot onto this vector. So then it becomes a point in one-dimensional space. This is a two-dimensional data, project onto this only one vector, then it's going to point in one-dimensional space. And this is going to be the point in one-dimensional. This is going to be the point in one-dimensional space. So it means instead of projecting the data in this direction, suppose if I project the data perpendicular to this direction, okay, then in such cases, there is a overlapping. I mean, it is not possible to classify. So ultimately, anyway, this is, I mean, there are certain situations where I need to have that information. So particularly that is called as a linear discriminant analysis, which we will see at the later stage. But as far as PCA is concerned, it does not have a knowledge of the class labels. So therefore, it aims in finding only the principal direction. So therefore, it is classified as a unsupervised learning algorithm, where you do not have a class labels. Okay, and clustering is one such, which Zaid Ansari has already pointed out. Okay, so and this is the spread of the data, and you can definitely classify. It maximizes variance of the projected data and minimizes mean square distance between the data point and the projections. What do you mean by that? Minimizing the mean square distance. So take the difference between these two. I mean, this point and this point, this is what the difference between these two. And I can compute the distance between any 2 points using different distance measures. So I'm sure you are already familiar with the different distance measures which are used in the context of either classification or in the context of clustering mechanisms. Could be an Euclidean distance, well known, so Malana base, or a cosine similarity measure, etc. Different distance measures are used, and maybe we judiciously decide which distance measure is most important. In fact, there is a contribution from Computer Science Laboratory, University of Mysore, on distance measures, particularly with respect to the fuzzy data. Naginsam and Guru has worked on that, and they come out with a novel distance measure to which explores the fuzzy and also symbolic data representation for the same. However, here, as all of you may be familiar, Euclidean distance, I can compute the Euclidean distance between these 2 points, and that is going to be minimum. So in a way, it is a kind of optimization problem. So PCA is one kind of optimization problem. So therefore, can very well be solved. We will see how exactly it is linked to what is called as a constraint optimization problem, which can be easily be transformed into unconstrained optimization problem through the concept of what are called as the Lagrange multipliers. So it boils down to finding the eigenvalues and the eigenvectors, and the solution is that in fact. So anyway, in general, the philosophy of PCA is to find the orthogonal projection of the data onto low dimensional linear space. But how do I find that is a question. So in a way, to say here, the idea is given a data in d-dimensional space, project onto lower dimensional space while preserving as much information as possible. In the sense, simple example, I have a 3-dimensional data. Can I find a best 2D representation of the same? So in the previous example, here I have given you 2-dimensional data. I am trying to find out 1D representation of that. In a way, to some extent, the data space is reduced, computational complexity can be increased. So therefore, in the case of, in the context of bandwidth, and how exactly this is similar to the original data is a question. Therefore, the question of what is called as minimizing the mean square distance comes into picture. So if the distance is approximately 0, it means that it is the best representation that we are having. But not all cases it is do possible. Anyway, if I consider this PCA to say in terms of the example, I'm transforming a 3D data to a 2D data. I'm transforming a 10 for 4D. It means that it is a point in 10,000 dimensional space. And can I represent an object? Let us assume that an object is having 10,000 dimensional, 10,000 values, what we say, what are called as the features. Can I just represent all those 10,000 by only 12? You may be surprised. It is too possible with the help of PCA, but how? How exactly we can do that? I mean, we are trying to choose a projection that minimizes a squared error in reconstructing the original data. And it is quite a common problem in the field of image compression. So how do I verify the quality of the compression? So when we classify algorithms into a lossless or a lossy compression algorithms, so PCA, of course, can be interpreted as a lossy. Normally, in general, it is called as a lossy compression because some amount of data lost is there. Otherwise, there is no point in employing PCA for the image compression purpose. I mean, there is some amount of error. I may not able to reconstruct the original data, but the data is visible. So that is more than sufficient for some class of application. Depending upon the application on hand, you may need to judiciously choose what algorithm is required for you. So for a medical field, probably I need to have a best compressed, what is called as, which is a lossless would be required. On the other hand, for networking, data transfer, let us say, for example, video communication or visual surveillance systems, you can think of what are called as these PCA also as lossless mechanisms where computation of PCA while transforming the data from node side to a server side, because the problem can be analyzed or a solution could be given using in different context. For example, IoT, I'm taking the sensor data. I'm having the sensors which has less computing power rather than transformed, but also the bandwidth problem is also there. Then can I think of what is called as a kind of edge computation? People now talking about that. And I'm sure you will get to know about that also in days to come. So where I can just convert or minimize the data and subsequently transfer so that the bandwidth can be efficiently utilized. Server may not be heavily loaded in such situations. So it means we will find so many applications we can think of relating this PCA in different domains too, of course. So ultimately, pictorially, when I say this PCA, it seeks a projection that best represents the data. So it is a kind of what is called as a data representation, I would say, where the data that you are going to represent is more discriminative in nature. That is most important. I cannot take, because definitely I do not have any control over the sensors when collecting the data. The sensors could be a camera, the sensor could be a scanner, or the sensor could be a conventional surveillance systems, and so on and so forth. And I do not have any control over those sensors that they give me the data, but can I convert the data into a what are called as extract the information from the data such that the data is most what is called as compact form. So therefore, sometimes this principal component analysis is also called as reconstructive subspace analysis techniques. So when I say it is a subspace, you are having huge amount of data space which will be mapped to low dimensional space. That's what. And how do I get such subspaces? It is again projecting the data onto principal component vectors. So principal component number 1 points to in the direction of the largest variance. As you can see here, these spread of points, as you can notice here, this is a spread of points. Okay. And then where is the maximum variance is, of course, is in the direction, and perpendicular to that. And as we have keep on discussing perpendicularity, and it means to say that they are orthogonal to each other. When I say such, what are called as the principal component vectors. And why that constraint to be satisfied, we will see in the course of our discussion. So orthonormality is inferred, of course. So they are a kind of what are called as the basis vectors, we would say. So in the sense, these two-dimensional data could as well be projected onto principal component, onto this vector, and that may be the best representation from the point of view of classification. So each subsequent principal component is orthogonal to the previous one. This is the PC1 and this is referred as PC2. It is a two-dimensional space. We can go or visualize 3D, and beyond that it is not possible, as you know that. We cannot think of imagining, say, beyond three-dimensional data, of course. People are also telling four-dimensional data visualization, but still in reality, probably we have not come across such situations too. Maybe in simulated laboratory environment it is available. Anyway, so I just mentioned in the course of our discussion, it's also referred as a dimensional reduction, a feature extraction, or a feature selection mechanism that finds an application in these kind of problems. It could be a trend or a factor analysis, that is a business analytic process. The data need not be a image type. So it could be a noise reduction, so the data could be a speech. It could be a data compression. The data again could be a speech, or could be the audio, the speech or the audio or the video data, or it could be the image or surveillance system. PCA finds application in all these domains too, apart from conventional standard well-known physical chemistry or say also. So now coming to the basics, how exactly I can think of. Now we have come to a stage where in which I am interested in finding what is called as the best basis, or what is called as a vector that transform the data into a low dimensional space and that maximize the variance. That is what is my requirement. How do I have how do I estimate from a given data vector which maximizes the data? That is most important. Let us formally come out with what is called a solution to this particular stated problem. Let us assume that an X denote an m-dimensional random vector representing the object of interest. It could be of any object. To say that it can be a speech, or it could be a simple mobile device, or it could be a laptop, or it can even be the face, or it can be a fingerprint. I basically given examples related to these what are called as image data, because we are working in the field of pattern recognition and image processing. So it is in general, it could be any kind of some data of m dimension. It is a real valued vector representation of a dimension m. When I say it is a dimension m, that is number of values are going to be m in nature. So for example, I would say a person is defined by height, weight, color, and his qualification. So there are 4 values there. It is a 4-dimensional feature vector. So I'm telling you these even small bits and bits just because of the reasons that we even sometimes when we start reading pattern recognition image processing course, and when a professor says it is an m-dimensional vector, in fact it goes out of our head. What he is speaking, what do you mean by saying n-dimensional vector, something like that. And what is meant by a random vector? So its existence is there. Probably again you are supposed to have a basic knowledge on probability and random variables. So I insist, if at all you are interested in carrying out a research work or even continue a research work, you need to have at least refer to some books on probability and random variables, which definitely is very, very useful. And I'm sure, as Dr. HSN already discussed, Navy Bayes classifier, where the decision is based on the probability theory again. Anyway, let us assume that now XC denotes an dimensional random vector. And given these data in m-dimensional space, can I identify an insignificant data, an irrelevant data? So, I mean, we are now putting question by ourselves. Given such huge amount of data, a vector, real valued vector, where m is very, very large, and question arises, where do you go for returning the data? Because nowadays computational efficiency, I mean, GPU, all those megaflops operations are possible. But still, as far as the video or the audio or the amount of data we are getting from different applications is very large. So computationally, they are very very intensive. So therefore, we are trying to extract meaningful, eliminating some unwanted information. So redundant information, we would say, or insignificant information. But is it possible to eliminate such insignificant feature values from a given data? It is not possible in the given space itself. So therefore, so in a sense, random elimination is possible. So is it possible to eliminate the data randomly? So in such case, I am supposed to eliminate the mean square error. So mean square error in the sense that if they do not contribute, if those set of values which you have eliminated results in approximately zero variance, then definitely I would say that yes, such what is called as the feature values could be eliminated. But definitely in real scenario, I cannot think of having such redundant data in a particular place. I have given you m-dimensional vector. This is the problem with online teaching. I cannot write on the board and explain. And either I should use myself and giving the picture and again all on the screen. Anyway, that is one limitation. That's why I told you in the beginning, having online class is also merits and demerits, of course. Eliminates travel, but again, these kind of problem. I have m-dimensional data, and can I eliminate, let us say, from assuming m-dimensional data, say vector x, so x1, x2, etc., xm naught, and from m naught plus 1 to m, can I eliminate them? But what is the guarantee that that insignificant information lies in m naught plus 1 to m? I don't know. It may be in the beginning, or it may be in the middle, or it may be in the end. So which is not possible. That's what we will say here. When I say elimination of insignificant data in the n-dimensional space, in the original, I mean to say from the sensor data itself, it is not possible. If at all I want to eliminate, I am just verifying the mean square error. If the mean square error happens to be say 0, then it means that they could be eliminated, which we cannot decide in X itself. Therefore, can I find a kind of transformation? Can I estimate a transformation T, which transform this given what is called as the m-dimensional vector X onto another m-dimensional vector A, where in which such insignificant data is located at some place. In fact, I'm sure by this time you thought of some solutions for this. So the solution, as you already aware, probably the people who are from the domain of signal processing, electronics, electrical engineering, and all those fields, so know that the Fourier and DCT could as well be used. When you transform the data, given a m-dimensional vector, I can use a DCT, where in which maximum amount of information is available in the first few what are called as the components, DC components, as you know that. And I am taking these, of course, also I would like to say at this stage that I refer to what is called as Professor Sen Gupta, IIT Kharagpur, So delivered these lectures long back, 2012, on principal component analysis, when he is discussing about neural networks. So therefore, those who are interested further can look into those. I shall give you the link for all those at the later stage. So now coming to this point, design of some transformation, orthogonal transform. When I say it is a Fourier transform or a DCT, discrete cosine transform, it's again based on the fixed kernel. When I say it is based on the fixed kernel, it means that any function, any value can be represented as a sum of sine and cosine terms. That's a well-known theory by Joseph Fourier. As you know that most of you studied image processing or even in signal processing. That is, of course, a prominent playing a prominent role nowadays from signal analysis point of view. And cosine terms could also be used as a fixed kernel over there, and I can extract only the few components. From the first few components are good enough, and the rest can be discarded. So, I mean to say that there exist already what are called as the some standard transformation techniques to transform the data onto a lower dimensional space. In a way, I am just converting or employing this Fourier transform or a DCT onto such vector and fix up only first few components or extract only first few components. So that in fact is a solution to the problem. Then is it necessary to invent something new? So question, of course, it is always a research bent of mind. Why don't we invent based on the data that I am having? Please note here, based on the data that I am having, can I find an optimal transformation function? Is it possible to find an optimal transformation function which of course changes with respect to, when I say it is an optimal transformation function, I am trying to estimate the set of, I am trying to find out the set of what are called as the basis vectors which are orthogonal to each other, such that I can project the data onto fewer such basis vector and of course reduce the dimension of the data. It's an interesting issue in that way. I mean, now the kernel is not fixed, it varies with respect to the data that you are having. In fact, that's what in PCA does. The PCA builds optimal basis set of vectors, what we referred as normally the eigenbasis, that is generally called as eigenbasis, set of what are called as the eigenvectors, we would say. It estimates the set of eigenvectors based on the data that I am providing. So it is because I do not have any control over the sensor data, so therefore I am using a kind of what is called as optimal transformation function that converts these what is called as high dimensional data onto lower dimensional space using projecting that high dimensional data onto these what are called as the basis functions. That is the idea over here. And what are the set of basis vectors to be considered? Do I need to consider all the basis vectors? If at all I am having a matrix of size m by n, so definitely you'll be having m number of eigenvectors you would get. Then is it necessary? Then it is going to be same as the original dimensional data only. So therefore few eigenvectors are good enough for me. How do I choose such few eigenvectors? So it depends upon the amount of energy that is residing within each eigenvector. How do I decide the energy? The energy is nothing but the spread in the principal component. So if the more the spread, I mean the variance is maximum, it means that it captures the variance better. It captures the discrimination much better. Therefore, you are supposed to project the data onto eigenvectors associated with largest eigenvalue. And why this issue is important? Because we argued with Professor Guru when discussing PCA during our research studies. I said, sir, why don't we project only on the maximum, eigenvectors associated with eigenvalues? Why don't we go on minimum? Then he simply said, you experiment. Then we conduct experimentation and got 20%, 30% result, which infers that definitely doesn't carry significant information. We are supposed to carry. Therefore, again, he asks us to read the theory beyond that. Don't simply come and argue and do not think something which may not work out. So mathematical basis, in fact, is important over here. That's what I'm trying to mention, highlight here. That is the concept of linear algebra would be playing a role here. I mean, our own optimal transformation function that we are trying to do over here. In fact, PCA does that particular job, extracting or identifying a set of basis vectors. We will see that. I mean, let's come to the analysis part. How do I estimate such what are called as the eigenvectors? So we assume that there is a random vector which has a zero mean. That is, expectation of x is equal to 0. The question is, how do I have a vector or how do I convert a given vector such that it is having a zero mean? So you may simply need to do the mean subtraction. That's all. From a given vector, do the mean subtraction, then definitely e of x is equal to 0. So you can verify the same. For example, I have given you 1, 2, 3, 4, 5, 5-dimensional vector. The mean is 3. Then subtract each value from 3, it becomes -2, -1, 0, 1 and 2. Then definitely if you find the mean, it becomes a 0. That's how you can make, given a random vector, I make it as a 0 mean. That is expectation of x is equal to 0. And why these things are required? So these things are required in order to frame a solution to the problem, to make it more easier. That's nothing more than that. So we do the normalization, we do the scaling, do mean centering, just because from the point of view of analysis. Okay. So in general, I cannot get from the sensor data having e of x is equal to 0, but it is do possible to transform the data such that e of x is equal to 0. Okay. Now, given these what are called as the random vector, say x, let us assume that let there be a unit vector of dimension q, where in which I am projecting this vector x onto this q, such that I will get a what is called as the for the time being assume that there be a q which denote a unit vector of dimension m onto which this vector x is to be projected. So what do you mean by saying a projection? It is nothing but the inner product of the vectors x and q, which is defined in this way. That is, A is equal to, either we can write x transpose q or q transpose x. Either way you can write. That is m by 1. You know that x is a dimension of m dimensional vector, m by 1. Then we also mentioned that q denote a vector of dimension m. Therefore, it is again m by 1. Its transpose is nothing but 1 by m by 1, it becomes 1. I mean to say that it becomes a scalar quantity. And either way, you can write. And what is the condition to be satisfied? So in the sense, I am trying to estimate, given a, let's say, a randomly specified unit vector, which we are supposed to compute based on this data, subjected to, when I say it is a unit vector, definitely this norm is equal to 1. What do you mean by saying norm is equal to 1? Q transpose Q and its square root. So results the value 1. That's what the condition to be set. I mean, these are the assumptions for the time being we are specifying in order to come out with eigenvectors and eigenbasis is the solution to the problem of what is called as a dimensional reduction. So under the assumption that the random vector x has a zero mean, definitely it follows that the mean value of projection of A is also 0. It means to say that we are defined A is equal to x transpose Q or Q transpose x. Then what is the expectation of A? I mean, with respect to that projected data also. With respect to that projected data, so as you can see here, you do not have, of course, I mean, cannot make, we are intended to make modification to Q, therefore it can be taken outside. And A is, as you know, that it is nothing but Q transpose X. So E of A, Q transpose X, and apply E of X is equal to 0. This is what the condition to be satisfied. So obviously, when I take the variance of A is therefore same as its mean square value, which we can write in this way. That is E of A squared. So just expand this. So when I say E of A squared, Q transpose X, X transpose Q. And simplify this. So because you cannot think of expectation onto these unit vectors Q transpose and Q. So onto this data you can make modification, that is Q transpose E of XX transpose Q. It is a simple what are called as the mathematical equations analysis, that's all. And let X transpose represented by R. So now variance is now defined as Q transpose RQ. What is this R is? In fact, this R is the correlation matrix. Sometimes we also call it as variance covariance matrix, correlation matrix of the random vector X, formally defined as the expectation of the outer product of the vector X with itself. How do I define R? R is defined as E of XX transpose or X transpose X. We can write in either. And please note here, this R is a correlation matrix because you are multiplying X with itself, its transpose. It is going to be symmetric in nature. So in fact, there is a argument also by, I just recollected this juncture, Professor Mallesh from the Department of Physics, our teacher. He is from the physics domain, but he is very interested in these mathematics, linear algebra. He said you cannot expect always a semi-definite matrix, semi-definite symmetric matrix. Then it is going to be an ill-posed problem. And in fact, people have given a solution to such ill-posed problems also. And of course, it is beyond our discussions right now as such. But it is an interesting, I mean, if at all you want to carry out a research work even in physics or in math, that's how we can relate. This principal component analysis in statistics is called as a multivariate data analytics. So it is a contribution of the mathematicians and the physicians to the field of computer science, machine learning, artificial intelligence. So very, I mean, excellent, we would say. When you complete this discussion, you will come to know how well people have thought to come out this their own transformation function, given a set of data. Okay, now what we are trying to, we mentioned here it is a symmetric. When I say a matrix is symmetric, definitely I would say R transpose is equal to R. So this condition holds good. And when I say it is R transpose is equal to R, it has a lot of interesting properties. What are the kind of interest? Because that is very important for our discussions too. And that such interesting properties, you may need to refer to matrix algebra or a linear algebra. Therefore, if at all you are a beginner researchers, your first course, maybe in, if you want to carry out a research in machine learning or so, pattern recognition, image processing, your first course should be on matrix algebra, random theory, kernel, and so on and so forth, optimization theory and all. Because that gives you basic insight, and most of the papers published in IEEE, one or the or Springer or elsewhere, whatever the case it is, at some point of time they use these as a basis. When I say they are symmetric matrix, then that interesting property is going to be used at the later stage. I will tell you at that point. When I say it is symmetric, A transpose or B can be, as will be written as B transpose or A. I mean, that holds good. So given any two random vectors A and B, so A transpose or B can be written as B transpose or A. So I mean such, there are different properties are there, but one such property that we are going to use in our discussion would be that. Okay. So now let us assume, now we have come to this point where R is a correlation matrix. So represented by what? Represented by, as you can see here in the earlier discussion, sigma square, that is the variance, Q transpose RQ. So now the variance sigma square of the projection A is function of some vector, that is unit vector Q, in the sense here, as you can see here, I'm representing this variance through these what are called as unit vector and trying to make modifications to these. I mean to say that use unit vector because I do not have any control over this R, because it is the data that is being collected from the environment. So I'm devising some function. Let us, it is just a representation, renaming. Representation psi of Q is, say for example, sigma square. So which is nothing but Q transpose RQ. So on the basis of which you may think of variance probe. What do you mean by that? I mean to say that you basically change to some extent, I mean perturb, normally that terminology that is being used in signal processing domain is the perturbation. That is just change, slight change in the unit vector, direction of the unit vector. Make some modifications in the direction of the unit vector, check whether the variance is going to maximum or not. So that's what we are trying to say over here. And in what direction it is supposed to be changed. Because you know that when I say it is a unit vector, of course, I can, we have so many important properties to be satisfied. So in what direction it is supposed to be changed is of paramount significance. So and that is called as what is called as the variance proof. Change in some values. Can I just change the values of Q? And when you are changing the values of Q, it is supposed to be orthogonal. That will come to why it's supposed to be orthogonal. Please remember this point. When I say it is psi of Q, let's say it is Q transpose RQ. Next, to be considered as a problem of finding those unit vector along with psi of Q as extremal value. I mean to say that we are trying to estimate the local minima. Normally, maxima is not considered because in the course of discussion, people mentioned that there could be, I mean, maxima could be infinite, whereas minima, as per you assume a parabola or a kind of what is called as a bowl, where if you leave a ball within that what is called as a cup, then it finally lands at some location. So taking what is called as the a path in this way, and subsequently it sits or settle at some point. So means to say that that's what when I say it is a physical significance. So we are trying to estimate the minima rather than the local maximum. So I mean we are trying to say here when I say it is a variance proof, make some minor changes to the unit vector that you are having. Let that minor change be a delta q, and psi of q plus delta q be approximately same as psi of q. I mean, you are changing a little modification, not y. Maybe that's why it is referred as a delta q. Small change in what is called as the given unit vector, say called say q. And from the definition of various proof, I mean, what is psi of q over here? Psi of q is nothing but q transpose rq, and you extend the same for this. What is psi of q plus delta q? Psi of q plus delta q is nothing but q transpose. Q is now replaced by q plus delta q, or, and again q is there. If you refer to the previous slide over here, q transpose or q. So replace q by q plus delta q. It is q plus delta q transpose or q plus delta q. Then simple multiplication operation. Q transpose RQ 2 times delta Q transpose RQ. See, this is where we have used the property of symmetricity nature of what is called as R. Otherwise, you cannot get these values. I mean, I cannot add if at all it is not symmetric. And delta Q transpose or delta Q is negligible because we already mentioned delta Q is very, very small. Therefore, definitely this doesn't give any significance. I can equate. So as you can see here, it is approximated. Eliminating this term, it results with Q transpose RQ plus 2 times delta Q transpose RQ. And what is Q transpose RQ? It is nothing but psi of Q. And what is psi of Q? Psi of Q is nothing but psi of Q plus delta Q. Therefore, these two gets vanished. I mean, they equated. Now, if I shift this, it's going to be 0. In a way, 2 times delta Q transpose RQ. So that is, we results with this equation. Delta Q transpose RQ is equal to 0. I mean, this is one important equation for our derivation, subsequently for PC. Please remember, delta Q transpose RQ is equal to 0. So the Euclidean norm of the vector that remains equal to unity, because we mentioned q plus delta q is very small. Therefore, we assume that so q plus Euclidean norm of is equal to when I say it is having the value 1, it means to say that so delta q plus delta q transpose multiplied with q plus delta q is equal to 1. That's what it influences. And again simplify this. And this is a negligible quantity which you can eliminate. Q transpose Q is equal to 1 because Q is a unit vector. And since it is a unit vector, Q transpose Q is results with 1. Therefore, I results with what is called as delta Q transpose Q is equal to 0. Now, what do you mean by that? This is of course very important for us. When I say delta Q transpose Q is equal to 0, it infers that I told you there is a slight change we are supposed to do in the direction of with respect to Q. I mean, delta Q should be a small change with respect to the unit vector that you assume. And when you are making or changes to such delta Q, I mean to say q with certain value delta q, then it is supposed to be orthogonal to q. Because when I say q transpose q is equal to 0, it means that they are orthogonal to each other. So here also this holds good. It means that the perturbation delta q must be orthogonal to q, and therefore only a change in the direction of q is permitted. That's what the inference that you could draw from this particular equation. So in a way, if you look at the previous discussion, we have basically, you analyze now equation 1 and 2. Okay. So I'm having here delta q transpose rq, and we are having an equation q transpose q is equal to 0. So this term is equal to 0 and this term is also equal to 0. But the only difference between these two equations 1 and 2, delta q transpose q is equal to 0, and earlier we are having delta q transpose rq. Okay. So therefore there is a matrix here, a correlation matrix R here. So how do I equate 1 and 2? Because although they are equal to 0, I cannot simply equate that they are equal. So in the sense, I need to scale the values, that the scaling factor be, let's say for example, lambda, and equate it to 0. In the sense, delta q transpose rq, that is equation 1, it is equal to 0. And let's say I put some scale factor called say lambda. So delta q transpose q is also equal to 0. Then from 1 and 2 I can represent in this way with scaling factor lambda. So alternatively, what we are trying to do over here, we just take out delta q transpose, which is nothing but now simple transformation of this given equation. Rq minus lambda q is equal to 0. So what do you mean by that now here? Definitely this cannot be 0. Therefore this quantity should be 0. So when I say this quantity is going to be 0, it infers that Rq is equal to lambda q. In fact, this is the equation that counts the unit vector q, for which variance probe psi of q has external values. And Rq delta q is a well-known eigenvalue problem. So it's Rq is equal to lambda q is recognized as the eigenvalue problem commonly encountered in the linear algebra. So therefore I told in the beginning itself. So now it boils down to what? Boils down to finding the set of what are called as the eigenvectors and the associated eigenvalues such that I can project this correlation matrix R. Okay, I mean I'm basically estimating these eigenvalues and the eigenvectors from this correlation, from the given data itself. I'm estimating or finding the basis from the given set of data and project onto what? The eigenvectors associated with largest eigenvector. That is lambda 1 is associated lambda maximum. So which we are writing, of course, this statement could be written in this, I'm having m number of eigenvectors because it is a correlation matrix of dimension m by 1. Therefore, we are having vector is x is a vector of size m by 1. Therefore, R is now a correlation matrix of size m by m. Since R is a correlation matrix, symmetric, semi-definite, I can expect m number of eigenvectors and m number of eigenvalues. You are supposed to project this m-dimensional data onto, let's say, first few eigenvectors, what are called as qj, associated with larger eigenvalues, that's all. I mean, take only lambda 1 or lambda 2, or lambda 1, lambda 2, lambda 3, or lambda 1, lambda 2, lambda 4, maybe some k, where k is very much less than m. In the sense, you are transforming an m-dimensional vector x onto x k-dimensional vector, let's say, I would say, for example, x dash, which definitely is having a low-dimensional space. Therefore, this PCA is also referred as a dimensionality reduction technique. So, associated with largest eigenvalue, there is a maximum variance. Subsequently, it gets reduced. So, means these eigenvectors associated with these at the tail end, what are called as the eigenvalues, of course, carries no significance. To say that, I can as well eliminate them. I mean to say that I'm representing this entire information in a different form. That's all, nothing more than that here, where lambda is nothing but a diagonal values of lambda 1, lambda 2, etc., lambda m. So matrix Q is orthogonal. I mean, the kind of what is called as notation that are used in the literature. So orthogonal matrix are also sometimes called as unitary matrix in the sense that it is a column vectors, which are nothing but the eigenvectors of R satisfy the condition of orthonormality. Means they are orthogonal to each other, which forms what we referred as earlier, as we mentioned, it is a basis vector. Project this m-dimensional data onto these basis vectors. Basis vectors associated with largest eigenvalues. You can take only few largest eigenvalues and the corresponding eigenvectors such that the data gets reduced and could be represented in a compact space. So in a way, I'm eliminating what is called as may not be in the original space, but in the transformed space. And in the transformed space, okay, and in the transformed space, you can definitely has the dimension vector m itself, but the last what are called as the values, you can even verify the same because I will be discussing the implementation issue of the same, which you can also verify that the last few what are called as the values in a given feature vector of dimension m does not carry any, I mean, the variance is almost going to be 0. So therefore, you can eliminate or chop off such values in the transform space. That is the what is called as the philosophy behind this principal component analysis. Okay, this is from the point of view of reconstruction. What we so far discussed is the analysis, and this is again referred as the reconstructive subspace. I mean, to construct the original data. How do I do that? How can I obtain R? So what we referred in literature, it is called as a spectral theorem, and maybe these things would not be required at this stage. We can just keep these. So in a sense, the two most important findings in the course of our discussion is that we are estimating the eigenvectors of the correlation matrix R pertaining to the zero mean random vector X that define the unit vectors Qj, representing the principal directions along which the variance probe will have their maximum values. And the associated eigenvalues define the extremal values of the variance probes. I mean, these are the two important findings with respect to our discussion. So graphically, what we are trying to do over here. So given a two-dimensional data, because we cannot think of demonstrating beyond 3D. So given a two-dimensional data which spreads in this direction, I am projecting the data onto the principal vector. So I mean onto this vector rather than onto this vector. In fact, this leads to one of the best solution and published in a journal as I'm sure at this juncture. I should recall the amount of time that we have spent on implementing the line detection algorithm. And this is the idea. When I say it is a line detection algorithm, approximately there is a spread in the maximum direction, I mean principal direction, and the spread in the other direction is going to be almost 0. This is the idea floated by, I mean coined by Dr. It is his original contribution, and it is well cited paper, a simple and robust line detection algorithm based on small eigenvalue analysis. And this is what the argument that leads us to such discussion. I mean, we have used a small eigenvalue rather than a larger eigenvalue. In most of the cases, people think of maximum eigenvalues, but we explored the computer science laboratory, University of Mysore, come out with a solution where they explored small eigenvalues to estimate the lines in a given image, to estimate the corners in a given image. Dinesh has in fact worked on that, Dinesh Punitanda, where they extract the corners from the given image, exploring the properties of these eigenvalues and eigenvectors. Very interesting. So I can pass on those papers too if you are interested. Okay. Just to say an example. So given a two-dimensional data, what we do? So we estimate the covariance matrix. And how do I find the covariance matrix? So given x1, x2, etc., two-dimensional vectors now. So this covariance matrix is nothing but I'm supposed to first do in our discussion what we have made, do the mean centering first. Why do I need to do mean centering? I should do mean centering to make E of x is equal to 0. That is xi minus m, the transpose. This is a correlation matrix. Number of samples are 8, therefore it is so. And which gives me what is called as variance covariance matrix, also referred as a correlation matrix. And given this correlation matrix, what is the next step? The next step is, this is what mean center data. Now you can see the mean value is going to be 0 over here. The mean is going to be 0 here. That's what, when I said is a mean center data. So that is E of x is equal to 0 over here with respect to this information. And summation of x, estimate the variance covariance matrix. Once you have the variance covariance matrix, so find out the eigenvalues and the eigenvectors associated with this. And I'm sure this you have solved in your 10th standard days. That is what is called as the characteristic values and the characteristic equation. Obtain a characteristic equation. If the characteristic equation of degree 3, it means that there exist 3 roots. Characteristic roots we say. So characteristic roots are nothing but the eigenvalues. So and every eigenvalue will be having corresponding what is called as eigenvector. I mean, this variance covariance matrix, what is referred as, that is, let us say A minus lambda is equal to 0. That is, I am evaluating the determinant. So determinant of A minus lambda I is equal to 0. I is an identity matrix. Then solve for lambda. So lambda, when you solve for lambda, it is now it is a 2 by 2 matrix. Therefore, it is a polynomial of degree 2. When I say it is a polynomial of degree 2, it results with 2 roots, characteristic roots. When I say root, what do you mean by that? So the value of the function vanishes at that point. Okay, at lambda 1 and at lambda 2, it cuts the x-axis at 2 different places. That's what it in turns means. So the function vanishes at that point. So associated with these 2 eigenvalues, I can obtain the eigenvectors and project the data onto an eigenvector associated with a largest eigenvalue. So given these kind of what is called as data distribution, definitely this is the principal direction and this is the secondary diagonal element. Principal diagonal and secondary diagonal. Principal direction and then what is called a secondary second principal component vector, that you would say. So I'm projecting the data onto this. Therefore, definitely the classification is discrimination is more possible. I mean, your 2-dimensional data is now becomes a point in 1D space. That's what the advantage. This is with respect to 2D. We can as well extend it to m-dimensional also. The same is true. So graphically, let me just explore it. What do you mean by saying graphical representation? So this is the given data. I'm trying to fit the data in the principal direction, and this is in the next. Projecting the data means to say that just multiplying the these set of points by the corresponding vector, eigenvector. That's what means to say a projection of the data onto a point to obtain a point. Okay. So means for a given data set, assuming this is the data that I had given, set of points in a 2D space, estimate the mean. The mean, as you can see here, represented by a red color. Okay, given this set of data, it is represented by a red color. Now, do the means entry. When you do the means entry, it is nothing but shifting the coordinate positions. That's what is happening over here. So, okay, I shifted the coordinate position from here to here when I do the means entry. Okay, now the data distribution goes in this way. New coordinate system looks in this way. Okay. Calculate the direction in which the variance is maximal. So in the sense, definitely the spread of the data is in this direction. So therefore, the variance obviously is going to be high in this direction. Variance is going to be lesser in this direction. If the variance is 0, it means that second minor component analysis, major component analysis. These are the terms some of you may be familiar. Okay. Calculate the direction in which the variance is maximal. Then project the data onto that. And of course, this is to be repeated. And definitely, they are orthogonal to each other. That is, we already proved. Whenever you make changes in delta Q is supposed to be delta Q transpose delta, I mean, say Q is equal to 0, we mentioned, orthogonal to each other. So then rotate to a normal position, I mean to the original position, and then project the data, showing us the maximal variance. I mean, what we have discussed in, I mean, theoretically, graphically, we can, this is what is going to be happen at what is called as illustration, visualization point of view, we can specify so. Now I have a set of points here. I'm projecting onto the principal vector over here. So all become now a point in 1D space. They are now a two values. I mean to say that a vector represented by two value is now represented by only one value. But still there is a discrimination. I mean they are very well separated. If at all I project onto the minor component, definitely there is a overlapping. You can verify the same. So for example, take the data which I had given earlier. Here, if I project onto the minor component, then there is a overlapping. This and this will overlap. This and these two will overlap like that. But however, when you take this, what is called as in the main direction principal component, definitely it is. And when I say it is the largest eigenvalue, in fact, it represents the spread in the data. This is what the spread. Okay. That's what the, I mean to say that representation of this. So now come to the algorithm. This is where, of course, finally we boil down to. I mean, basically, I will have what is called as a data matrix, which has m rows and n columns. Given this data matrix, I do normalization. Why do we do normalization in general? As you know that the data may be captured from different sensors, from different units. Therefore, the data is supposed to be normalized, and there are different ways of normalizing the data. So taking the maximum and then computing the minimum, and then it is possible to make it as value lies between 0 and 1, such that it's invariant with respect to what is called as data scaling factor. Okay, and then once you have this, you can make it as unit variance scaling. Each is a represent the standard deviation, of course. This is another way of scaling too. I mean, ultimately, in simple terms, maybe what you have discussed, given a data, make it mean centered. And before means entering, you can make it, say, for example, unit normalized. Or you make it the value lies between 0 to 1. Once you have that, compute the variance covariance matrix. How do I compute the variance covariance matrix? It is nothing but given x transpose x will give me what is called as variance covariance matrix. And it is a semi-definite matrix, symmetric matrix. Therefore, it is guaranteed that eigenvalues and eigenvectors exist. So extract the eigenvalues and eigenvectors associated with that. How do I compute the eigenvalues and eigenvectors? As we are discussed in the context of what is called as the in the context of 2D data. So that procedure is to be followed. That is identifying the characteristic vector and characteristic equation. So a minus lambda is equal to 0. In that way you can compute. And then since if it has of m dimension, then you will be having m number of eigenvectors, because it results with m eigen values. So obtain the covariance matrix, compute the variance, and once you have this variance covariance matrix, compute the principal components, and then project the data onto maximum, I mean to say that few principal component vectors associated largest eigenvalue. This is the overall what is called as the algorithmic summary. Okay. I hope, I don't know whether because there is no, I mean to say that feedback, I could see some faces saying yes, faces saying no, things like that in offline. However, here only I should say that you are getting, assume that you are getting so. So face recognition problem would be one such example, which I am planning to take, maybe with little amount of time, paucity of time. Anyway, we will go through that. Given a matrix, we convert into a vector form. Do all these with respect to all the training samples. That forms what is called as a training matrix X. Given this matrix, estimate the what are called as the, you can normalize it, identify the or compute the variance covariance matrix, then estimate the what is called as the principal component vectors, project this entire matrix onto only few principal component vectors, such that the data gets reduced. In the sense, suppose if the matrix of image, now this is an image data of size, let us assume 100 by 100, then it is a vector of 1000, 10,000 dimensional space. You consider the principal component vectors, maybe first 10. Then if I project the data of 10,000 onto only 10 eigenvectors, then this entire data is represented with only 10 values. So similarly, the other person is representing 10 values, 10 features, I would say, 10 features, 10 features, and so on. Therefore, your knowledge base is going to be reduced. And that knowledge base definitely contains the discriminative information And how do I argue that it contains a discriminative information? I can say because I projected onto the data where the mean square error is, it is a maximal variance. So that's what it intends. That's how we can say that your projected data is more optimal. So this is reconstructed data, from the point of view of synthesis using first few principal component vectors. This is also an interesting issue. When I go with Guru, he said you should implement. I don't know, then it looks like a ghost face. In fact, for us, when in the first instance, we read more than 20, 25 times that Morris and Nair paper, 3D object recognition paper, that gives the idea how exactly you can obtain the solution. You have to read such high impact journal papers because that definitely gives you a lot of courage. Say that knowledge on the area that you're going to work on. So maybe relatively more better when I reconstruct with more number of eigenvectors like this. So this is an example to illustrate. Similarly, an image compression. This is the given butterfly image. So where it is initially, when I consider some region of dimension 144 with say for example L2 error. So if it reduced to 60 dimension, we may not able to get that much difference. Probably I can still identify it as a butterfly. Similarly, if I represent with 16 dimension, you can still say it is a butterfly. There are some applications where I need not represent with original 144 dimension. Smaller dimension is good enough. It reduces the space and also increases the computational complexity in terms of equation, equating or finding similarity gets reduced. Maybe with only 6 dimension, but still from the distance, I would say it is a butterfly. But you can see that there is a little bit, say that artifacts, as you can see with only 3-dimensional. See here, this is how it looks. But still from the farther distance, I could conclude, although there are certain artifacts. You can see, these kind of images, sometimes there is a disturbance in the channel. So, network error that we would say normally. So, to say that the data, complete data is not, say, for example, available over there. With only one dimension, that is the first principal component vector, if I consider, this is how it looks when you do the synthesis. Synthesis is nothing but reconstruction over here. Similarly, I told you that is useful in eliminating the noise. So, it is nothing but a smoothing operation that you would say. So, let's say it is a salt and pepper noise. It's a rainy season, something like that we can assume, salt and pepper noise. Then in such cases, I can model it to some extent that gets eliminated with 15 PCA components. That's how it is. But please note, PCA is not the ultimate solution all the cases. It has certain problems. So what exactly the kind of problems it has? Take this kind of data. So now, what is the, let us assume this belongs to class 1, these samples belongs to class 2. Please note here, PCA is an unsupervised learning algorithm. So therefore, it does not have the knowledge of the class labels. So obviously, when I estimate the principal component vectors associated with this entire set of data, so it in fact associated with the maximal variance is in this direction. The spread in this direction, maximum spread. Therefore, when you project this 2D data, this is a class 1 data and this is a class 2. Two different people's characteristics that you extracted, a number of people that you obtained, only 2D data. Then there is a overlapping, clear overlapping that you could get. So therefore, misclassification is going to be happen. Instead, if I have a class level information, maybe this projection of this data onto this direction is more appropriate. And that is achieved through one more supervised learning algorithm called a Fisher linear discriminant analysis technique. It's a kind of classification mechanism very equally interesting, wherein which they have a knowledge of the class labels. And PCA does not have the knowledge of the class labels. Therefore, it definitely gives some bad results. As a researcher, people also think of giving solutions to these kind of problems also. What kind of solutions that one can think of? Can I explore PCA for these kind of problems too? Or can I explore, because there may be a situation where you don't have the knowledge of the class labels. Then in such cases, can I modify PCA to achieve the results for this? Yes, it is too possible. Okay. Let's say the data could be of this kind. Definitely, I cannot think of linear classifier. For that purpose, there is a solution to what was called as the kernel principal component analysis, probably which I am not going to take up right now. So this is the spread of the data. So what you can do is you project the data which is in 2D to higher dimensional space. Now the data spread is this. This is a class 1, this is a class 2, this is a class 3. Definitely I can think of what is called as, I cannot definitely think of in this space a linear separable. I mean, distinguish between these three classes. Therefore, project the data onto higher dimensional space. Now I can find, see here, when I project the data onto higher dimensional, maybe 3-dimensional, so I can definitely get a decision surface over here. That is what through what is called, achieved through what is called as the kernel principal component analysis, which is again much more interesting works people have carried out. So, which is of course outside the scope of discussion. So to summarize what we did, it's a orthogonal linear transformation that transforms the data to any coordinate system such that the graded variance by any projection of the data comes to lie on the first coordinate and so on. Permits us to reduce the dimensionality of the data set, identify the strongest patterns in the data, captures most of the variability of the data, and eliminate noise. I mean, these are the characteristics of the principal component analysis. So this is what, as far as the theoretical aspects are concerned. I just wanted to tell you that, in fact, nothing is more powerful than the human brain. Although we are training the minds, machines, definitely it cannot replace the human mind. So that's what Swami Vivekananda told. So thank you very much at this juncture. But just recall and recollect the various steps that we have executed in order to extract the principal component vectors. And the problem what we are going to discuss is with respect to the face recognition. Okay, here I am having what is called as the it is with respect to face recognition data called as oral data. This oral data set is well known and extensively used in the literature. Okay, let me just take that and show you. So there exist what are called as, I think screen is visible there, no, right? You can find the description of various databases that people explored extensively. And one such is this oral data set. And there are maybe some link issue is there. Anyway, if you go through here, there are standard databases that are available. Probably it is better if you conduct experimentation when you are submitting your research work on the standard data sets. And if data sets are not available, and if you are able to create, if there is an environment in your laboratory to have such standard data sets, is wonderful. I mean, to create a data set. It's also, in fact, a contribution to the research community. We can think of that. So as far as this particular oral data set is concerned, there are, in fact, each one is a folder, S1, S2, S3, S10, and so on. Yes, 40. I mean, there are 40 people, and each 40 persons are given 10 different what are called as the phases. I mean, with varying illumination, with a beard, with a spectacle, etc., with the different hairstyle, these faces are captured. In fact, I just wanted to tell you again here, this is a PGM file. And PGM file, as you can see, how do I identify the PGM file? As you can see, I don't know whether it could be visible or not. P5, P5 stands for a PGM, and next is 92, that is the stands for the number of what are called as the columns, and next is the value 112. So it stands for what is called as the number of rows, and next value is 255, so it stands for what is called as a grayscale image. I mean, these are the characteristics of the image, and subsequently the data. Data is in the ASCII form, as you can see here. And you can directly read this information through any of what are called as the standard right now available tools. Maybe in Python using OpenCV, image read could be used. Even in MATLAB, IM read function could be used. And similarly, most of the programming languages, even Java also supports image reading through a tool called an OpenCV, which is available plugged in, could be plugged in with respect to any of the standard recently available programming language. Even it is true with the case of Python also. Okay. So now this is what the description, of course. So I have 10 phases associated with all the, I mean, say each person, and there are 40 people. This is, you just, I mean, aware of this in order to conduct the, or say to discuss the experimental part. There are 40 people, and each person is represented by 10 different faces, captured in different environments, captured in different daylight conditions. Today you may come with a different colored shirt, different hairstyle, tomorrow with no beard. That may be the case. Therefore, I just simulated a real scenario, that's all. And some samples are used for training and some samples are used for testing. So again, deciding the number of samples, in fact, also a reason for what is called as the accuracy calculation. So in the first talk, Arivino has pointed out that k-fold cross-validation could be used in order to judge the correct, what is called as the size of the data set. So cross-validation is one such means. You can take such accuracy measure based on the such data and decide which are the best training samples to improve the classification accuracy. Anyway, you can randomly choose, and let's say 6 samples from this and remaining 4 samples for testing. Randomly choose 8 for testing, training, and remaining 2 for testing. Things like that. Randomly choose 1 for training and remaining 9 for testing, which is definitely people have addressed that single image is training is possible. People made an attempt in that direction too. Okay, and then recognition accuracy would be too less. That may be the case because there may be certainly overlapping as far as the feature vectors are concerned with respect to different training samples. They may look similar. That is what earlier pointed out, that intra-class similarity and inter-class variability. So that problem would be erased. Anyway, so in simple overall to say, there are 40 people and each people represented by 10 different samples. You may choose some number of samples for training. You may choose some number of samples for testing. With that issue in mind, okay, what we are doing over here is, you come back to just to the last statement over here. Probably these some of these things you may need to refer to the Python manual that is available, where name is equal to main means to say that that interpreter looking for what is called as the main function. And this is just a bookkeeping routine to say that if the number of arguments that you are going to specify not enough, then generate a warning message. It's as good as what is called as a kind of exception handling. And I'm going to store the data in a directory called say results, which for that purpose I'm using an utility called say OS. So OS, there are again a library. I mean to say that it is as good as saying in C language include stdio.h, which in turn contains many functions. So here, instead of saying include, I would say here import. Okay, import OS, import CV2. I mean, this instance contains a set of what are called as the library functions meant for some specific purpose. For example, I want to read the data. Then I need not write a program from the scratch, a function that reads the data from the file. So I can use the file.h, that is utilities that are available. Similarly, NumPy, of course, Dr. Arivino has discussed, mentioned the role of all these what are called as these what are called as the packages, or the which in turn contains set of function. In Java language, it is called as a package. Package in turn contains various functions. As NP, it is just a renaming convention. That's all, nothing more. Okay, I mean to just a shortcut renaming by NP rather than calling it as NumPy. And various functions are available within NumPy, similarly random, shell utilities, system, CV2. CV2 is mainly for OpenCV, the functions to manipulate the image data, because we are now dealing with face recognition problem. So now coming to this lower part of the code, I just brief in terms, this part is just to a kind of what is called as a big bookkeeping routines. In the sense, check whether from which directory you are reading the data and where you are going to store the results. So because I should store the results at the later stage from the point of view of analysis, where should I store? If the directory does not exist, store it in a directory called say results. That's all I'm doing. Then you recall the algorithm. What is that we did? We just take, as I told you, there are 40 people and then there are 10 phases or so with each and every person. So therefore you take, say for example, 60% for the training and remaining 40% for the testing. You can select randomly out of 10 phases for each person, randomly select 60%, I mean 6 phases, and remaining 4 you can use for the training. So, testing. And whatever the algorithm, the data that I am used for training should not be used in the testing. It's a common sense. Otherwise, definitely you'll get a 100% accuracy over there, as far as that particular classification is concerned. So, I am calling a function called an eigenphase, passing the corresponding argument over here. So, I mean, the first argument is passed as a parameter converting to a string type which to a function called say eigenphases. What does it do? It does the task of computing the eigenvectors and creating the knowledge base. How do I do that? So, I am supposed to read the data and then represent in the matrix form, normalize the data, then make it mean centered, then normalize the data, compute the variance covariance matrix, estimate the principal components, and I mean when I say principal components, vector and the eigenvalues, eigenvectors and the eigenvalues, choose the first few eigen vectors, then project this what is called as the original data onto the eigenspace, create what is called as the, I mean to say that I would normally call it as the eigenphases. That's what the term that is being used extensively in the literature. Call it as an eigenphases. Eigenphases now contains a dimension of the data is much reduced, because originally, as I showed you earlier, 92 by 112, that is the size of each and every image. So when I say it is 92 by 112, if I convert it into a vector form, then definitely it is of size 112 by 92, which is very huge. So can I just reduce the dimension of the data, which can be stored in a knowledge base? So, and how do I decide the number of eigenvectors? So for that purpose, you can compute the energy. So how do I compute the energy? So what you can do is, how much is the variance with respect to first and the second? So similarly, first, second, and the third. First, second, third, and say fourth with respect to fourth, with respect to fifth, and so on, you can compute. That is lambda 1 over lambda 2. Similarly, lambda 2 over lambda 3, and so on, you can verify, and summing the same. And at some point of time, it's negligibly 0. So, I mean, you can chop off the last principal component vectors. That's what it in turns means. That is the task of what is called as this particular function. Next is the evaluation. Evaluation is nothing but calling the corresponding what is called as the taking the test set, then check whether to which class it belongs to. If it is the same class, I would say it is a correct classification. Otherwise, it is a misclassification. I mean, we are basically computing only the accuracy over here. You can estimate from, of course, precision, recall, and then F1 measure. Values could be obtained, which would be an assignment, which I will tell you at the later stage, because that helps you a lot. And also, you know that how to compute a confusion matrix. And based on the confusion matrix, how can I obtain estimate, precision, recall, and the accuracy? And similarly, the ROC, because they are the metrics to decide how good your method is. Okay. So, I mean, this is the basically the training part and the test part. So in the case of training, I am reading the data, obtaining the eigenvalues, eigenvectors, projecting the data, and storing in the knowledge base. What I am doing in the evaluation phase, I am taking the set of phases, project the data onto those eigenspace and then comparing, perform the Euclidean distance, check whether to which class it belongs to. And based on the correct class belongingness, then I would say that it is correct classification, otherwise it is a misclassification. And finally, I compute the accuracy. I mean, how many are correctly classified and how many are misclassified. That's what. So which will give me the accuracy evaluation function does. So now let us come to this, what is called as the eigenfaces function. When it comes to eigenface, I define it as a class. Okay. So eigenface, and you define some variables over there. Bookkeeping, of course. So faces count, that is number of faces are 40. Right now, the directory is initialized to dot, that is the current directory. Number of training phases, that is I told you 60% for training, 40% for testing. And obviously, this train phase count and the phase count gives me what is called as number of samples in the training set. Okay. And then M is 92 dimension, N value is 112. Therefore, the dimension of the feature vector is going to be M by N, that is 92 by 112, which is very, very large, of course. And these are the, of course, the initialization part. Initialization part that will tell you the kind of what is called as the nature of the data that you are going to have. That is, as far as the overall data set is concerned, this is the nature of the data. Okay. Then define a function called, of course, as you know, init is a function which is nothing but, those who are already familiar with C++ or Java, I'm sure you know what is a function of the init is. It's basically a constructor which instantiates the objects with the respective values. And by default, explicitly, we are specifying a parameter called, say, a self. And unlike other C++ language, why do we specify this parameter? It is as good as saying this pointer. You know the function of this pointer. And here, there's an explicit specification. That's what the argument that we have seen in the debate. People have spent why self is required. I mean, they made it more explicit, unlike C++, where this is implicit. So now phase directory and passed as a parameter. And I would say here, as you know, that as far as C++ is concerned, in order to access the variables over here, as this is assumed, this dot phase directory, this dot energy is going to be specified. So otherwise also you can write directly. And there is nothing like what is called as a private variable, as you are aware as far as the Python is concerned. Self dot phase directory and then energy and similarly training IDs. So this is the initialization part, okay. And you take a vector. What should be the size of the vector? The size of the vector is of size M by N. And it should be converted into one-dimensional form, because I told you now a matrix image is of size 92 by 100, 112 by 92, 112 by 92 matrix converted into a vector form. So this is the function, that is a shape is equal to, I'm just converting this, this initialization does the task of initializing this vector L of type, say, float. I mean, it is any operation that you need to do, as you know, normally to be converted into a floating representation, float point representation. So 64-bit representation we have specified. You can specify float 32, etc. also. Doesn't matter. So I am representing now, it is a vector, a row vector. The mn number of what are called as cells are there. That's what it in turns means. Now read the image. This particular portion is to read the data. Cursor image, I mean the first, second and so on. For face ID in the range of 1 to face count, that is up to 40. So this is selecting the random among 1 to 10. Then take it ID. Then reading the corresponding what is called, this is a string concatenation operation. So which will basically gives you the location of the image. So it is location in face directory. Phase directory, let us say overall data set, and within that it is a phase ID. Phase ID, as you can see here, it could be 1, 2, etc. and so on. Okay. And then subsequently, training ID. Training ID is nothing but it can be a first phase, second phase, and so on. Yes, see here, yes is there. Yes is concatenated with phase ID, that is which person you are trying to take. And within that person, which sample you are taking. and appended by .pgm because the files are of type PGM files. It is just a string concatenation operation to get the name of the file. That's all, nothing more. I mean, the image data. So then, of course, I just this is a kind of testing. I just wanted to check whether we are reading the data or not. And finally, I am reading the data. So CV2 image read path to IMG 0. It can be the value 0, it can be the value 1, or it could be -1, which stands for grayscale, binary, and so on, color image. So you need to look at the L function IM read under a package called say CV2. Okay. So once you have that data, so that is called as the image data. It can even be displayed. Right now I made it as a comment. So this says that IMShow is a function which displays the image data. Automatically a window gets opened and the image can be displayed, which is not required at this stage now. So next, this is to convert into a vector type, then appending the same to what is called as the L. L we have initialized a vector. So vector, then this becomes a first row. So as you know that CUR of image, all the values, it is a column vector now, entire data is, then update the image, cursor image by one value. So that this L now is nothing but the matrix X as I told you. And once you have this matrix X, what is the next step we did? We made it mean centered. How do I do the mean centering? Estimate the mean. And once you estimate the mean, subtract from what is called as L. And this is a shortened rotation with respect to the C language also. That is minus is equal to, that is L is equal to L minus mean of the image. So it becomes what is called as a mean centered data. This particular part of the code is to make the data mean centered. This part of the code is to get the mean of the image. On the right hand side, you will see the comment also, get the mean of all the images, subtract from all training images. Then the mean subtracted image, once you have this mean subtracted image L, then do the compute the variance covariance matrix. How do I compute the variance covariance matrix? L dot transpose, of course, with L, of course. Okay, NP, that is NumPy library. Within that, there is a function package called say matrix, and within that, of course, which pass object as a parameter. Now L is an object. Having the function called say associated with the object, it is now I'm calling a function. That is the beauty of the object-oriented program. That is, rather than passing data as a parameter to the function, we are passing function as a parameter to the object. That's why it is called as object-oriented. Transpose, and here it's of course L as it is. So L transpose L, that is variance covariance matrix, which we referred as a symmetric matrix. Once you have this real symmetric matrix, make it of course unit normalized. Then once you have this data, compute the eigenvalues and the eigenvectors. So that is now C. I am passing C as a parameter to a function called say EIG, which is defined in an NumPy library. So EIG of C. So this function is available. We can directly use that, which gives me eigenvalues and the eigenvectors. See here, eigenvectors and the eigenvalues. Once you have these eigenvalues and the eigenvectors, they may not be sorted. Therefore, I am interested in selecting only the first few eigenvectors associated with largest eigenvalues. And this is the procedure. I mean, as I told you, evaluate the energy content of each eigenvalue. Based on that, you can, if the energy is going to be depleted, I mean, if there is no variance, then it as good as saying there is no energy. So, and I mentioned, we have mentioned here, the energy's value is approximately 85%. I mean, if the reconstruction accuracy is nearer to 85%, that is sufficient for me to classify to which class a person belongs to. So you can vary this value and see what is the classification accuracy. That's what. So it may select a few number of eigen vectors. Then after that, what you are going to do? So once you selected such eigenvectors, you project the data onto, see here, L, given matrix L, I am project onto those eigenvectors, which is stored in what is called as a W. W is my now knowledge base. This is all as far as the training part is concerned. In simple terms, read the data, mean subtract the data, okay, compute the covariance variance matrix, extract the eigenvalues from the eigenvectors, project the data onto the eigenvectors, store it in the knowledge base. That's all the training part. So that ends what is called the eigenphases. Then I'm going to evaluate it. So as far as evaluation is concerned, okay. So again, you are supposed to take the set of samples which are not in the training set, and this is but this particular block does that job. Okay, you please go through. I will share this code with you all. So, and again, it is self-explanatory. What you can do is on the right side, we have given the comments also. So it read the phase, check whether it is in the training set or not. If it is not in the training set, it is going to be considered for the a candidate sample for testing. And I'm going to classify. How do I do the classification? Classification is just computing the Euclidean distance between the test vector and the projected vector, and then check whether to which class it belongs to. So result is equal to test correct gets updated, and I'm going to write onto a file called, say, using the function f, right? And f, as you know, that is initialized to results file. Results file is nothing but a attribute results.txt. That's all in a folder called, say, results. This is the name of the file, and this is the directory. And I'm opening a file under the write mode such that the data will be written onto that particular file called, say, result.txt f.write. Okay, what is the corresponding ID and so on. And once you have that, you found the count, I mean, convert into percentage and display the accuracy. This portion does that job. It prints the corresponding accuracy, how much they are. Okay, so evaluate portion is over. Given a 60% of the training samples, 40% of the testing samples, you are going to get the what is the corresponding accuracy. So in order to execute this is of course in the Spider. You can use any framework. There is no restriction constraint that it should be done in only Spider. There are PyCharm, I believe, right? Yes. PyTorch and so on, right? Yes. There are different tools that are available. You can test the same. So in order to execute this, of course, you need to give the name of the file. Okay, that is face recognition.py, and the corresponding directory where exactly the data set is loaded. I told you the data set is loaded in a directory called, say, ORL data set. Okay, so therefore pass this as a parameter to this function. So run face recognition.py d drive ORL dataset / okay. Some intermediate results are displayed. Don't worry about that. Okay. Finally, it gives me an accuracy of 95%. Let's say I run once again. It gave 95%, of course, once again. So now 94.375. Why it is the difference? The difference is due to randomness in the selection of the samples. So means, so probably if I run multiple times, so 96.25. So you can run 97.5. Take the average of 10 runs. That gives me what is called as the corresponding result. And don't worry about these values because this is just for our checking, because it gives you at the time of testing some values which are non-zero also. That's why we just take these intermediate. And this is an important for me. Correct is nothing but 97.5. And this is the accuracy we are getting. And the results are stored in, of course, corresponding what is called as this particular attribute results.txt. Okay. This code will be shared with all the participants. Please try with different what are called as the values. What are the assignments which you need to submit tomorrow? Okay, to the coordinator. And evaluation report would be submitted maybe in the evening or so. I mean, what are the assignments here? So we have tested with ORL data set. So we will also give you the other data set, okay, like alley data set. You need to test on that, number one. Assignment number 1 is to test on different data set, that is ALE, which is available for downloading. We will also share in the Google Drive. And with respect to this present code itself, you vary the energy. You vary the energy from 60 to 80, 85 or 90. Okay. And obtain the accuracy. What is the accuracy that you are going to? That is number 2. And number 3 here, we have used here what is called as the 60% and 40%. And you vary this component also. If I give 80% training set and 20% test. Similarly, 30% for training and 70% for test. So you fix up the such parameters and let us see how well you are going to analyze it. And what may be the corresponding recognition accuracy. Change these parameters and report the results. You may find difficulty to, of course, with respect to again implementing ALE, maybe for a beginner. Of course, for the people who are already familiar with this, they can easily do so. And with respect to different phase data sets, because all these parameters to be changed, you need to study the structure of that particular data set. All those things would be required. And straight away, as far as this particular program is concerned, change the number of training samples, testing samples, and see the results. Change the energy level and see the results. And also, one more important is do the reconstruction. See what is going to be happen. With 85%, what is the reconstruction error? And similarly, with 90%, what is the reconstruction error? And with let us say 30%, what is the reconstruction error? That helps you to understand the internals of the principal component analysis. Okay. So probably I can stop at this stage. Exactly 4:20. Let us say not at 4:20. So we would just conclude and say that this is how, of course, PCA could be very well explored in various domains, not only with respect to face recognition. So wherever you are finding large, huge, or say m-dimensional data where m is very, very large, you can think of exploring principal component analysis, not blindly, but with judicious consciousness within your mind, such that it works. It works only when what? When the data distribution, maybe you cannot make out with 2D, of course it is too possible. So simply or blindly don't say that PCA is imply PCA, things like that. That may not be a good way, but the overall philosophy is to say that it selects the best features out of the given set of samples. So in a way, it reduces the dimension of the data. Therefore, we coined it as dimension reduction, and it reconstructs the data. Therefore, it is a reconstructive subspace analysis technique, and it is a feature selection mechanism. Let me stop at this stage, and I take this opportunity to thank the organizers, Dr. Sharmila, Mohammed, Ganesh, and the team who coordinated very excellently, including the time management. Thank you very much.
Thank you very much, sir, for such a wonderful session, sharing the in-depth knowledge about PCA. So now we move on to question and answer session. That is, first question is, what about information loss and accuracy due to data dimensionality reduction in PCA?
Yeah, that's definitely I have answered this indirectly or indirectly. Information loss is there. The account of loss could be decided based on the energy that is being captured, as I told you, based on the number of principal component vectors. There is always a trade-off. So more the number of eigenvectors, better is the lesser the loss of information. Less the number of eigenvectors, more the loss of information. But in terms of representation, that is storage constraint is concerned, time constraint is concerned, it is going to be efficient. So it is supposed to be judiciously decided. Maybe validation factors could be considered depending upon the application, depending upon the energy that you need to have. So you can think of that. So let's say, for example, as far as image compression is concerned, it is good enough for me if the reconstructed image is approximately 90% same as the original image. You can fix up the energy as 90%. So that decides what is called as the loss. 10% loss is there. That's what the inference.
How is PCA different from a linear regression approach?
In a way, actually, as far as linear regression is concerned, we are predicting the values for a given what is called as the unknown sample, right? So, I mean, it's basically a kind of classifier. We are classifying to which class a particular sample belongs to, and of course, the estimation is based on the prediction to how closely is associated a new sample, how closely associated with a. It's altogether, I believe, a kind of classification problem. Here is a data transmission problem. Okay.
Thank you very much, sir. Now I request Professor Ganesh Pai to propose vote of thanks for the day 3 session.
It was a great session, sir, on the topic principal component analysis for dimensionality reduction. I'm sure our participants have got an inside understanding of PCA and its working. The concept explanation and the visual representation helped us a lot in understanding the concepts clearly. It was a very clear and detailed explanation on PCA along with its application in various areas. On behalf of Department of Computer Science and Engineering BASE, I extend the gratitude of having Dr. B.H. Shekar as a speaker of the session. There were a lot of takeaway from the session. I'm sure our participants have benefited a lot from the session. Thank you, sir. Thank you very much.
Thank you. Thank you. No
Thank you,
offline,
sir.
no. So, no offline.
Thank you, sir.